All right, I'm going to solve some of the problems in the electrostatics packet that says electrostatics-potential, and we're going to be looking at electric potential. And before we can really look at the problems for electric potential, we need to remember what electric potential is. So I'm going to draw my four square to kind of keep in mind how these concepts relate. And the upper left-hand corner is force, and then there's field, and then there's electric potential energy. And then there is potential, which is symbolized with a V. So here's electric potential down in this bottom right-hand corner. It's the least familiar to us in terms of being able to understand it because it's the least related to our concept of gravitational, where the other three really do match up with gravitational in a way that we can kind of understand and conceptualize. But yet potential is the most useful to us when thinking about electrons and when thinking about circuit electricity. It's what we're going to use and call voltage. It's going to help us identify how much power or how much energy is in the battery. So it's really very, very important, and it dictates quite a bit of how the electrons and how the electrons move and how we think the field line, how we follow the field lines. So it actually becomes really important. What is mostly solved for in terms of electric potential is we want to relate it back to a concept that actually does have some bearing in physics, and that is usually back to potential energy, electric potential energy, or just potential energy, or a lot of times the question relates back to work. How much work is done, because work signifies a change in energy, and that energy has to come from somewhere, and we want to know about efficiency. We can relate this back to machinery and efficiency, and if the work done is going to get us back what we want to improve our efficiency rating for different circuits and such. So this is where we're headed, to this idea of how potential connects back to work. So we're really looking at this loop here from potential energy back to potential, which is good because it's going to give us a chance to practice quite a few problems just getting this idea down. Once we really understand how potential relates back to work, we can start thinking about how this is going to play out in terms of velocity, and where the connection here is through kinetic energy. We can think about the kinetic and potential energy changes, how when one goes up, the other goes down. So for now, we're going to concentrate on potential to potential energy and those types of transformations in terms of equations and getting some math down. And then we can start making the connection over to other more mechanic style problems. All right, so first thing we're going to do is number one. So number one is probably one of the most straightforward problems we're going to see. Number one says that if 1 joule of work, so they actually tell me that work is equal to 1 joule. If 1 joule of work is required to move 1 coulomb of charge, so there's my charge, and it's equal to 1 coulomb, between 2 points in an electric field, the potential difference between the 2 points is blank. So potential difference is V. Well, potential is V. Potential difference obviously is delta V. But delta V is what is equal to work. All right. I'm sorry. It's not equal to work, but it's equal to, how do I say this? It's equal to the change in energy per charge. So let me erase that so that doesn't affect you later. It's equal to the change in energy per charge. All right, so the deltas stay here. It's still in front of potential and the change in potential energy. All right, so we need to remember some formulas. So the way that we get from potential energy to potential is by dividing by charge. So what potential actually is, so the definition of potential, so this is its definition. The definition of potential is the amount of electric potential energy per charge. And this is the definition equation for potential. Now, this equation is not written like this on the formula chart on College Board. Instead, it's written slightly rearranged, and it's actually written as the change in potential energy for electric potential energy is equal to the charge times the change in potential. So all they did was rearrange this equation to make this equation. So they redefined potential energy as the product of the charge and the change in potential. So that's how they redefined potential energy. We would have defined potential energy as the charge times the field times the distance from the source. That's how we have been defining potential energy. But this actually is the opposite of the way we defined, or I guess just the mathematical equivalent of the way we defined potential. And so these are equivalent fractions, and it turns out that this one becomes a lot more useful to us when we're looking at circuits and when we're looking at when an electron or a proton is moving in a uniform field. So when we have parallel plates. So this is actually really handy to think of it like this for the electric potential energy. All right, so there is an equation written on the equation sheet from College Board, and they actually have potential as the equation, the equation is written as V equals KQ over R. So you can see right away that this equation here would not help us in solving our problem because we just don't have that information. We have work, and we could translate work back into K's and Q's, but it would be a very lengthy process of trial and error or proportional reasoning, and it would drive us crazy. So instead, we need to use our definition equation, even though it's not what's provided on College Board, but it is provided this way for us. This is one reason I can't stress enough kind of drawing this out and playing with the algebra here to see how they relate. You also, I gave you an equation sheet of just the electricity equations that go with this unit and then the mechanics equations and how they cross over, but it doesn't have all the electricity or the magnetism equations on your sheet yet. Do yourself a favor, cut those apart, move them around, write them down, play with them in some way so that they start to derive some meaning for you. Once you have your equation selected, it's not that hard. You know that work and energy, potential energy, or change in potential energy are basically the same thing. Work and change in potential energy are basically the same thing. And so now we're left with a very simple equation where if we're looking for our change in electric potential, it's simply equal to the change in energy over the charge. And in this case, our change in energy is going to be our work. That's the work that was done. That's the thing causing the change in energy. So we end up with 1 joule over 1 coulomb, and that's equal to 1 volt. So that's our first answer. 1 joule per coulomb is equal to 1 volt. So this is our first question, and it is about half of the problems in the packet, but we actually have a second question to look at as well. So in our second question, we're actually going to look at number 3. So number 3, and in number 3, the question is asked slightly different. It says, what is the total amount of work, so this time work is our question mark, what is the total amount of work required to move a proton, so this time we're moving a proton, so our Q is a positive charge, to move a proton through a potential difference of 100 volts. So our delta V is equal to 100 volts. So our proton is not 1 coulomb, and that's probably one of the biggest mistakes that I see students make, is they just start kind of getting used to the idea that it's a coulomb is a proton's a coulomb, or an electron, and that's simply not the case. A proton actually has the Q equivalent or the charge equivalent of an electron, and it's on our constants and conversion sheet, and it is equivalent to 1.6 times 10 to the negative 19 coulomb. So it's much less than 1 coulomb. So we don't have this problem nearly as simple as we did before. We can go to our equation sheet, and if we look at our equation sheet, we're going to find this formula, that V is equal to KQ over R. And again, this formula doesn't help me. What does help me, though, is my definition of potential difference. My definition of potential difference I can get from my Foursquare as the energy over charge, but I can also get this formula from my formula sheet because it's written as the change in electric potential energy is equal to the product of charge times change in potential. And this formula, which is the definition of potential, is actually the one I want to use right now. So in this case, I'm going to multiply my Q and my potential. So I'm going to have 1.6 times 10 to the negative 19 coulombs times 100 volts. So that means I just move my decimal point over, and I should end up with 1.6 times 10 to the negative 17 joules. So this would equal 1.6 times 10 to the negative 17, and this is joules. And the reason why is because a volt is equal to a joule per coulomb. So I'm taking a coulomb, multiplying it by a joule per coulomb, and I end up with a joule. All right, so the problems in this packet that are linked to this, these two formulas or these two types of problems, in addition to number 1 and 3, are numbers 6, 8, 9, 11, 12, 13, 15, 17, 23, and 25.